If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. In this video, we continue with hands-on implementation of isolation forest, which is a popular algorithm for anomaly detection. The dataset that we are using has been obtained from Kaggle, and it's known as the Ethereum fraud detection dataset. If you're familiar with cryptocurrencies, you would know Ethereum is a very popular cryptocurrency, and we are trying to find out if we have unusual observations in the data. Please note the objective of our exercise today is not to predict whether the fraud can be identified properly or not. This is not a supervised learning exercise. We are applying isolation forest. Essentially, we are not going to predict against a label. We are trying to identify if the independent features put together with the label, that means the overall data, contains some unusual observations. So isolation forest is an unsupervised learning technique. It relies on extra tree regressors that we've discussed in the theory part of it. Let's move on to the Google Collaboratory and we'll start working on the data there. All right, so we are at the Google Collaboratory and you can see a list of features that we had in our data set. We've just kind of listed them here. This data set is a feature-rich data. We have a number of features, about 50 plus features. And I've already pointed to the data source, which is known as the transaction data set. It's a CSV file from Kaggle. Now let's start by the basic tasks that we perform all the time. So we first begin by importing the basic libraries like NumPy, Pandas, Matplotlib, and Seaborn. And then we proceed to read the dataset, which is the transaction dataset. Let's quickly check what are the dimensions of this dataset. So it has about 9,841 rows and 51 columns. If we want to glance through the data types, we can see a mix of numerics and object type variables. So majority of the variables are ints and floats, and there are few variables, 3 variables in fact to be precise, 1, 2, and 3 variables which are object type variables. So most of the data is already numeric. Now we're just trying to rectify the names of these columns. If you see there is something unusual, you see a lot of spaces here when it comes to the names of these columns. It looks like we have spaces in the beginning of the names as well. This later on becomes a problem when you're trying to put these variables as input to an algorithm. At times it could become a problem. So we are just fixing the names of the columns. We are saying that we want to first of all strip any extra white spaces in the beginning or at the end of the name, and then within a name, wherever we encounter a word boundary, which is followed by one or more spaces and another word boundary, we are replacing that with an underscore. So essentially what we are saying is that these kind of entries, which have a word boundary here and then another word boundary here at the beginning, in between whatever be the number of spaces, we are replacing them with an underscore. This is kind of a regular expression treatment. And if we now check the features, this is how the features would look like. So you can imagine the second last feature here looked like this. It actually had a space in the beginning, spaces in between as well. And what we have been able to get out of this is that the earlier spaces have been eliminated and in between spaces have all been replaced with the underscore. So this is a small correction that we need if we have unusual feature names. Now let's proceed on to check the presence of duplicate records in the data. And we found a column called index in our data set. So generally, if you have an index column, that will be used to check for the presence of duplicates because that's supposed to be a row identifier. So we are using Pandas' popular duplicated method with the index as the input to the subset parameter and summing up the number of duplicate rows. So it says we have 5,112 such rows where the index is duplicate. In total, we had about 9,800 data points. This is a huge chunk. While our focus right now is on identifying the outliers or anomalies, we know this data set was eventually used for predicting the fraudulent transactions. Now we want to just check how's the distribution of the flag, which represents a fraud activity in this data set. So we are taking the flag column from the data frame and doing a value counts and normalizing, which means we'll see the proportion of fraudulent versus non-fraudulent cases. So in this case, if you see 78% of the cases approximately were non-fraudulent and about 22% cases were fraudulent. Now, since we have so many duplicate rows, it would have been very easy for us to just simply go ahead and drop the duplicate rows. But this is a huge chunk of the data and we cannot take chances. So what we're doing is we are checking for all the cases where we have the duplicate rows, what's the distribution of flag like? This is the distribution at an overall level, but for those rows where the index value is duplicate, what's this distribution like? Let's quickly check that. And you see this is very alarming because the distribution of zeros and ones in this case is very, very different. You had about 22% fraudulent transactions in the usual data, in the overall data. But in case of this specific filter, this number nearly doubles. About 43% of the cases are fraudulent. So in this case, it will not be wise to drop the duplicate rows. A, because this chunk is too much. Second is that the proportion could have a story that will help us at the supervised learning stage. Even though today we are not going to do this as a supervised learning problem, but anybody who does that as a follow-up would be in trouble if we actually drop these many rows which have a major proportion or contribution of ones of fraudulent activity. Now at this stage, so far we've checked for the presence of duplicate rows only on the appropriate column, which is what is supposed to be a unique identifier. But let's just say maybe index was not captured the right way in the first place. Let's say we check duplicates on the entire row. Do we actually have identical records in that case? The answer is no. That number is 0. So we only checked for the presence of duplicates through one column, which was right. But if you look at the entirety of the data, we don't have duplicate rows in the data. And as of now, we can drop the unwanted columns. Columns like unnamed 0, which is a serial number kind of a column. The index column, which is not serving its purpose. And there's a column called address. If you look at the address column, it essentially is a kind of alphanumeric code, a kind of a key. And that would not help us predict anything out of it. So let's drop these 3 columns. And then we move on to segregating the categorical variables from the rest of the data. We are using pandas select D types and applying a filter only with respect to objects. Dot columns stores the names of those categorical variables as an object called categories. That's what we have done. And now what we're doing is we are checking for the categorical variables, how many unique levels we have and how many missing values we have in these variables. So we are running a for loop for I in the categories, which is nothing but the names of the categorical features. Dot columns, the categorical column I would be just the name of the feature, unique values, and the missing values. So the first categorical feature, I can probably give a space here and run it again because it was kind of merging. Yeah, so the first categorical feature, ERC20, most recent token type, has 305 unique values, too many unique categories, and 841 missing values. The categorical feature, ERC20, most received token type, has 467 unique values and 851 missing values. So we have an idea. Why this is important to check the unique levels is because isolation forest is just like another algorithm. Though it is an unsupervised algorithm, it still needs the data to be in numeric format when it is given as an input. So if you have categorical variables, we'll have to figure out the right encoding. With these many categorical levels, of course, it will not be wise to do a one-hot encoding on these columns straight away or try to figure out an order because we would not necessarily know the right order. Likewise, let's select the numerical columns using select D type, this time including numbers, and we know majority of the columns were numerics. Within the numerical columns, we are checking for one possibility. Do we have features which are constant? A feature that does not vary, it has just one and the same value, would have the variance and standard deviation as 0. And a constant column would never be a good predictor for any purpose. So be it anomaly detection, be it the supervised learning, a feature which is constant, it means it remains indifferent irrespective of what the observation is all about. We are checking if we have such observations in our data which have their variance is equal to 0. We are just filtering those and trying to get those names. So df numerics var would take all the numerical variables and calculate the variance. Then we are specifically applying a filter that whenever the variance is equal to 0, we want to get the index or the names of those features. And we are storing them as constant columns. Why? Because it'll be easier for us to eliminate them all at once. Let's first run this, and then we can actually look at the names of those features which are constant. So we can quickly type constant columns. Here are the features that are constants. If we want to check how many such features are there, we can actually apply a length on this also. 7 such features are there in our data, to be precise. So let's move on to drop these 7 features. We are doing df.drop constant columns in place is equal to true so that the change takes effect at the original data. Now let's check the correlation matrix. Though isolation forest, just like other trees, is not sensitive to the presence of correlations, but we're just checking it if we have features which are kind of redundant, because we had about 51 features to begin with. We dropped 3 features earlier, the unnamed 0, the index column, and the address, and now we've just dropped 7 more features. So 10 features we've nearly dropped. Let's see if we have correlations present in the existing variables. So if we were to go through the code, we are selecting the numerical columns, Notice we are doing it again here because last time when we did, we had those features present which were constants. So the last list of numerics would actually have those 7 features that we have just dropped. That's why we are doing it again on the data frame after dropping those 7 features, and we are checking the correlations for all the numeric features. We are masking the upper triangular matrix here because you know that the correlation matrix is a mirror image. When we have too many variables, it becomes very difficult to interpret it. So we're just masking the upper triangular matrix. If we just change this to TRIL, it will be masking the lower triangular matrix. You'll see the upper matrix in that case. And then we are trying to see if we have correlation. So we may have some correlations, like you have this color beige here, which would indicate strong positive correlation, and a dark shade here, which would indicate a strong negative correlation. But like I said, because it doesn't matter for isolation forest, we'll not spend too much time on treating correlations at this stage. Let's move on to check the presence of missing values. This treatment is required for isolation forest as well because we can't give incomplete data. So what we're doing is that we are creating a heat map where the input is dataframe.isNull. Now, isNull returns an output which is a collection of booleans, true and false value. Whenever a value is missing, it will be a true. Whenever it's present, it will be a false. We are using a color map, which is cool warm, and we are not checking the color bar here. Just a snapshot of the data is what we're going to look at. If you see, this is one quick snapshot of the entire data. Imagine this as your spreadsheet, and these red lines essentially indicate the presence of missing data. Now, this is somewhat alarming because the data should be missing generally at random. So these points should have not been concentrated over a small rectangular space here. These missing values should have been spread out across the data. But looks like there's a specific pattern relative to these columns. And that will be interesting to investigate further. Either this has been eliminated on purpose, some of the missing data has been introduced just to make the point that we have missing data. That's one possibility. Other could be there could be something suspicious. Why there are certain records where consistently the same set of columns are missing. This is a very, very obvious pattern that we see here. So we want to explore this a little further. Let's first find out how many rows are there in our data which contain any missing value. So for that, what we're doing is that we are applying isNull, and then we are applying .ne. This .ne method would check for the presence of missing value. Even if one value is missing in a row, it will be considered as a row with missing value. If you have more values missing, it will still be considered a row with missing values. So this ne is going to check for presence of one or more, and then we do .sum on top of it. So we have 860 rows which have missing data. That's one side of it. But this still leaves us curious about the fact that why there is such a nice pattern related to the missing data, such a small subset of the overall data where you had that rectangular pattern. So we're trying to go a little deeper into this and figure out what's happening. This is the same missing value identifier thing that we saw. We've not added .sum here. We've just left it at isNull.ne. So it would at this stage return a Boolean, true or false. Then we are saying, let's take this to the .lock. .lock is something that's used to filter the data by a specific location. And then we are checking the flag column, which is actually the target column for the supervised learning task. Once again, we are not doing supervised learning here, but we are checking, is the target behaving very differently with respect to these values? Now, why we are doing this is because it is very easy for us right now to move on after treating the missing values, maybe with a central tendency. We could have easily imputed these missing values all at once. But we will be modifying about 860 rows in that case, which is close to 10% of the overall data. And modifying this much of data before even supervised learning is tried might not be a good idea. It will help us identify the outliers or anomalies as they are right now. But after modifying so much of data, would identifying anomalies be a good idea? May or may not be. So keeping the importance of the end objective that somebody might need this data for supervised learning, we will just try to investigate if we can go with a common treatment for the missing values or not. So what we're doing is we are checking the value counts or the distribution of the flag column or the fraud column here for those scenarios where we have missing value. And then we are also looking at the normalized output, which will tell us the proportion. So if you see, the breakup of 860 missing rows is such that 829 of these rows have anomalies. That 829 of these rows report a fraudulent transaction. And there are 31 such rows which don't report a fraudulent transaction. This is quite unanticipated. So 96% of the data within these 860 observations reports frauds, and only 4% of the data is free from fraud. Whereas if you look at the overall data level, we checked it earlier, I'm repeating the same code for the overall data, the value counts and the normalized value counts, this proportion was very, very different. In our overall data, the ones were not in dominance. The ones were lesser, the zeros were more. But in this data, where we have so many missing values, the ones are in dominance. And proportion-wise, the ones in this special subset is 96, whereas in our overall data, this was only 22%, less than 1/4. So definitely there is something really unusual with this data that's missing there. And so as of now, it looks like that if you find a record in this data frame which has any missing value, out of 100 such records, 96 times you have a fraud happen. Only 4 times it's a normal transaction. So we do not want to tamper this data at this level just because we want to do outlier detection. We don't want to modify so much of data because that will later on become a problem for anybody who's trying to do supervised learning. And this is a very responsible behavior we should keep in mind in the interest of our business. What we instead choose to do in this case is that we will try to identify the outliers in the remaining data, which is not affected by the missing value. So what we are doing is that this data frame, this till symbol missing mask. What is this missing mask? This is the Boolean output when you do df.isNull.any, access is equal to 1 for the rows. So we are essentially working with those rows which do not have any missing value. And this becomes our data frame on which we do anomaly detection. So we just printing the shape of this data frame and then storing it by the name of df sub. We'll be working on this here onwards. So we have 8,981 rows, 860 rows have been eliminated, and we have 41 features. Now let's separate X and Y variables. So essentially this requires us to drop the flag column or the target column from the independent feature set and store the flag column as the Y variable. We do the usual train test split. Please note this is not needed for isolation forest, but this is needed for a treatment that's still pending. Remember, we had 2 categorical variables left in our data, and we want to do their encoding. Now, the challenge is that those variables had too many levels, 300, 400 plus kind of levels. Of course, we cannot do one-hot encoding or an ordinal encoding for those variables. Instead, we'll have to rely on the target encoder. Please note, for this target encoder, you may have to install the library called category encoders first. Then you'll be able to import the class called target encoder. This target encoder is an encoding done against the target column. So you would need the target column, which is your Y variable, in a specific format. And that's why we did X and Y separation and split like this. So we are doing a fit transform on the train set, X train and Y train, telling that this is our independent set and this is our target column, and doing just the transform on the test set. Let's run this. So the output of this would be X train encoded and X test encoded. Our columns would contain all numerics now. We'll not have any categorical variable. Now for isolation forest, it is recommended that you bring the data in its entirety. You're not predicting Y, but you want to look at Y variable also as another piece of information that you want to utilize for isolation forest. So what we're doing is we are concatenating the X train encoded and Y train. Why did we split it? Because that's how the category encoder needed the input. Why are we bringing it back together? Because that's how the isolation forest algorithm works. It needs the Y variable along with the independent feature set. So we are concatenating with the axis one, which means we are bringing the Y column back to the data set. And so is the case with test. So we run this. And now is the time for us to call the isolation forest class from scikit-learn and sample. Isolation forest would require a few inputs. So there is a contamination variable. Now, contamination is the expected proportion of outliers in your data or anomalies in your data. If you do not have anything in mind in particular, you may leave it to auto. And this algorithm is intelligent enough to figure it out considering your specific data that you're trying to fit here. Please note, this generates the trees randomly. And we discussed about the extra tree regressor in the theory video that the extra tree regressor finds the partitions randomly. So we have to use a random state. Otherwise, the results might vary. Once we are done with instantiating isolation forest, we do a fit and we do a fit on the train set. We're not doing X train and Y train, the train set. What is the train set? It has both type of features, independent as well as dependent. Once the model has been fit, we do a predict on train and we do a predict on test. We're storing it by the name of anomaly train pred and anomaly test pred. The outcome of this, these predictions would be labeled as 1 and -1, whereas 1 indicates the presence of a usual value, a normal value, and -1 or a -1 indicates the presence of an outlier. Now we are saying let's count the total number of outliers. How are those found? The total number of -1s in the training data And so is the case for the test data. When we sum those up, we get the total outliers or anomalies in train and test set respectively. Let's print those and see what's the outcome like. So it has identified 219 anomalies in the train set and about 51 anomalies in the test. Now, one challenge that we have at this stage is that how do we actually identify what are these outlier values? What makes them so different? One is that we can, of course, do the descriptive stats of the data. One data which is normal, where these values would have been predicted as 1, and the other data where these values would have been predicted as -1. Are there significant differences with respect to some features which make them an anomaly? But if we try to visualize this, this is always going to be a little tricky because we can't visualize 41 features. And if you start pairing any two features randomly chosen out of 41 features, it'll be a very time-consuming exercise. This is where t-SNE comes very handy. We've done a separate video on t-SNE that you might want to watch if you want to understand how t-SNE works. So t-SNE is essentially an implicit transformation on the data. It is not an explicit transformation like PCA. It is actually an implicit transformation just for data visualization. So we are instantiating t-SNE and mentioning that we want to reduce the data to 2 dimensions. Again, we are mentioning a random state here, and we are doing a fit transform. Please note t-SNE would only be providing fit transform. It has nothing called as transform. So you'll not do it like a transform for test separately. For test also, you'll have to do a transform. What it does is it essentially reduces your entire data to 2 dimensions, just for visualization purposes. So which data are we reducing to 2 dimensions? We are reducing the X train encoded to 2 dimensions. Then we are creating a scatter plot where we are taking the first dimension as we'll get from t-SNE, which is with index 0, and the second dimension, which is with the index 1. And we are using the anomaly labels, those 1s and -1s that we got upon fitting the isolation forest, as a kind of hue here. Let's just run this code. It might take some time because t-SNE is a heavy transformation on the data, but it'll be able to give us some visualization, some idea about how these anomalies have been identified. This would still be just a try because we actually are not looking at every feature. We are trying to look at a projected space now, a transformed space now. So here is the t-SNE visualization, and you can see these points in yellow essentially represent the normal data points, and the other points here represent the outliers. It may not be very intuitive. When you look at this, you might say that these points should have also been marked as outliers. But please realize these are not the original features. This is a projected feature space. So you do not know what is the weightage given to any feature. You had 41 features. Should be happy that we are able to at least see something in 2 dimensions. So it's not so easy that we can intuitively eyeball the data and tell what value should be an outlier here, because you're seeing a crux of 41 features. But it kind of gives you an idea. There are certain points which have been flagged as an outlier. And if you want to see how it has been done for the test data, we again have to do a fit transform for t-SNE. Once again, to emphasize, we did a complete tutorial on t-SNE along with the clusters, because when we do cluster analysis, again, we are not able to visualize the data because there's so many features. So you may refer to that tutorial to get complete understanding on t-SNE. So here's how the test data outliers have been identified, the normal observations, and then we have the outlier observations. So to sum it up, we just learned how to apply isolation forest, which is an unsupervised technique to identify the anomalies in our data. It's more powerful compared to those typical techniques like the z-score based outlier detection or the IQR based outlier detection, because those techniques are limited to identifying the outliers at each column's level, whereas isolation forest has looked at the entire data. Why did I call it unsupervised once again is because we were not predicting against a target. We did not have an original label which said that this observation is an outlier. The target column in this data set, in fact, was the fraud flag. We never predicted that. We only tried to identify using the independent features as well as the flag column. We just tried to identify if a particular observation seems unusual. That's why it is unsupervised. So I hope this tutorial helps you understand isolation forest a little better. Thank you.